Tonight's journey drifts into the deepest shadows of the cosmos: black holes, event horizons, glowing accretion disks, and jets that carve through space like silent lightning. In the next moments, the universe slows down. Gravity bends light. Time stretches, and the invisible becomes knowable through its effects. If this kind of calm, science-rich storytelling is your space to unwind, tap like, subscribe, and turn on notifications. New deep space documentaries are always on the way. Welcome to Space Dreams Documentary. A black hole begins as a simple idea, then becomes a clean boundary in space. It is a region where escape is no longer a path that light can take. The first anchor is not the center. The first anchor is the edge that decides what can return and what cannot. In that region, darkness is not a coating laid over matter. It is a missing set of outward routes. A faint glow can still surround the absence. Light from nearby material bends and gathers into a thin ring. The scene resembles a silent silhouette set inside a dim halo. At this distance, motion follows the straightest available route through space and time. Far from any heavy object, that route looks like an ordinary line. Closer in, the same rule draws arcs. Light behaves as if the arena itself is curved. The bending is not a special choice made by light. It is the only straight route that remains in deeper geometry. A black hole can be described through this geometry alone. It is defined by the boundary where outward routes end. That definition stays exact even while the interior stays unseen. Now the view slides closer. A dark center holds the scene while the surrounding glow runs into smooth gradients. Some rays drift wide and depart. Other rays skim closer and curve back toward the darkness. The difference between departure and return narrows into a sharp threshold. That threshold is the main feature of the whole object. Event horizon is the boundary where escape becomes impossible. It is not a surface and it has no texture. It is like a mountain valley whose walls grow steeper with each step inward. Paths that once lead out begin to tilt back down. Even a fast arc cannot clear the rim once the slope becomes too steep. The idea matters because nothing that crosses that edge can send light back out. The boundary is drawn by geometry, not by material. Outside it, routes still connect outward to far regions. Inside it, every future route points inward instead. The horizon is not a place where matter breaks. It is a place where directions stop meaning what they used to mean. Just outside, an outward path exists. Just inside, an outward path does not exist at all. Escape fails without friction and without a barrier. It fails because the map of possible futures reshapes itself. A slow image holds on the boundary without drawing it. A sphere of darkness sits in a field of faint light. A thin, bright rim appears where many near-miss paths collect. The rim looks sharper than the glow behind it. Only a few concepts are needed to keep the picture stable. Gravity shapes routes. The horizon divides routes. Light traces routes. Near the horizon, light does not simply pass or fail. Some light can loop and still escape. Each loop delays the departure. Each loop also gathers many rays into a similar direction. That crowding is why a ring can appear. The ring is not a solid band. It is a pileup of routes that nearly fall in then slip away. The ring brightens on one side and softens on the other. The brightness changes with the surrounding light field. The shape remains tied to the same geometry. A gentle gradient runs from bright rim to dim background. The background field stretches into subtle arcs. Those arcs tell the same story as the rim. Light that begins far away arrives redirected. One number gives a quiet sense of compression. For a mass like the Sun, a horizon radius is about 3 kilometers. That is about the length of a long, unbroken river bend. A star spreads across an enormous span. Yet the decisive boundary for the same mass fits inside a narrow distance. Gravity does not change because the mass changes. It changes because the mass sits inside a smaller region. The horizon is not a wall added on top of gravity. It is what appears when gravity is concentrated enough that light has no outward route. Now the view pulls back again. The same rule scales up without changing its meaning. More mass means a larger radius for the point of no return. The effect stays absolute once crossed. The dark center is often described as a shadow, but it is not a shadow thrown onto a surface. It is a missing patch in the sky of directions. Light that would have reached far regions instead crosses the horizon. Those missing rays leave a dark disk in the view. A bright ring hugs that disk because many near-miss rays gather there. The disk and ring together create a clean geometry. That geometry is useful because it depends weakly on the messy surroundings. Gas can glow or it can fade. Dust can scatter or it can thin. The boundary still shapes which routes survive. Another slow image settles. The glow thickens into a smooth band. The ring remains thin. The dark interior stays featureless. A limit appears here that is not about effort. It is built into how signals work. No light can carry information outward after crossing the horizon. No wave can reverse course from inside and still reach the outside. The most that exists is inference from what happens before the edge. Light can show what circles outside, motion can show what remains outside. The interior remains hidden by definition. This is a limit of observation written into causality itself. The same limit also keeps the story calm. The outside provides patterns that can be read. The inside provides no direct messages. A final visual returns to the first silhouette. A ring floats around a void. The void stays quiet and complete. The surrounding glow drifts like a slow tide. At this distance, the scene feels almost still. Next, the story moves from definition to origin. Collapse turns ordinary mass into a boundary with no surface. The same geometry that draws the ring also draws the edge. A massive star drifts toward its ending without a sudden change at first. A black hole forms when the central support weakens and gravity takes over. In that region, the story begins with a balance. Outward pressure comes from heat and from crowded particles. Inward pull comes from the weight of overlying layers. For millions of years, the two effects match in a slow compromise. A calm image forms. Nested shells surround a dense core. Each shell glows with a slightly different softness. The center sits heavier than the layers above it. Fusion in the core provides heat that pushes outward. That heat keeps the core expanded enough to avoid a runaway collapse. A black hole is not created by strength alone. It appears when support fails and compression becomes unavoidable. When the core runs low on fuel, the heat supply drops. Pressure declines. Gravity does not decline. The core begins to contract. Contraction raises the temperature for a short time. That brief heating can light new fusion stages in surrounding shells. Yet each new stage lasts less time than the last. The core becomes a layered object under increasing weight. At this distance, the layers look like slow currents sliding inward. The density gradient steepens toward the center. The inward drift becomes faster because the weight grows as the core shrinks. The collapse accelerates because each step inward strengthens the next step. The core does not fall through empty space. It compresses through its own material. As density rises, particle crowding begins to resist further squeezing. This resistance is a kind of pressure that does not rely on heat. It is the stiffness of matter packed too tightly to rearrange easily. A mound of rounded pebbles on a sloped bank offers a quiet analogy. It can appear stable for a long time. Then one pebble slips into a gap. The whole mound settles into a tighter shape. Nothing pushes from the outside. The change comes from a rearrangement that reduces empty spaces. In the core, gravity plays the role of the slope. Once heat support fades, matter finds fewer configurations that hold it up. Bright layers fold inward in smooth sheets. The central region darkens as light struggles through rising thickness. The collapse becomes a rapid event compared to the star's long life. The inner core contracts in about 1 second. That is like the pause between two gentle waves on a quiet shore. In that short time, a region that spans thousands of kilometers can shrink far smaller. Density climbs beyond ordinary intuition. Pressure from particle crowding rises sharply. Sometimes that pressure is enough to halt the collapse. Neutron star is a compact remnant held up by particle crowding. It is compact with matter packed into a small sphere. Gravity near it changes quickly across short distances. It matters because it shows a collapse can stop without forming a horizon. When the mass of the inner core is too large, the halt does not last. The crowding pressure cannot fully balance the weight. Compression continues. A black hole forms not at the moment of maximum violence. It forms when compactness crosses a threshold. A dense central knot tightens while outer shells lag behind. The lag is important. Signals travel at limited speed. Outer layers do not respond instantly to what the center does. This delay allows two outcomes to coexist. An outward blast can begin while the center keeps collapsing. A pressure wave forms when the inner region stiffens and rebounds slightly. It is a front, not a wall. It moves outward through infalling layers. The front heats material as it passes. Some layers gain enough energy to reverse direction. They expand into a cooling cloud. Other layers do not gain enough energy. They slow, then continue inward. The outward moving front leaves a sharp gradient behind it. Density drops across the front. Temperature rises across the same boundary. The contrast creates a brief glow that can spread outward. Meanwhile, the center keeps shrinking. Now the decisive geometry appears. When enough mass remains inside a small enough region, outward routes for light end. An event horizon forms without a surface and without a signal from within. Just outside that boundary, hot gas can still radiate. Its brightness changes steeply with radius. Light behaves as if the space around the center is bending more strongly each moment. Paths that once curve outward begin to curve back. Past the boundary, no path can point outward into the future. A gentle scale shift broadens the view. The horizon can appear in a moment measured in seconds. The aftermath around it can unfold for years as expanding layers thin into space. Observation reaches a limit here. The collapsing center is wrapped in layers that scatter and absorb ordinary light. Even after expansion begins, the inner region can remain opaque for a long time. A signal would carry only indirect clues from outside the horizon. Timing information can ride on the brightening of the expanding cloud. Motion information can ride on how fast that cloud spreads. Yet the exact instant the horizon forms inside the debris cannot be seen directly. That limit is not a lack of patience. It follows from thickness and scattering. It also follows from the one-way nature of the horizon. Models must fill the gap between outer light and inner collapse. Those models depend on how matter stiffens at extreme density. They also depend on rotation and on uneven infall. The uncertainty is bounded, but it never vanishes. A dark remnant sits at the center of a thinning glow. Some material forms a curved ribbon that falls back inward. The ribbon narrows and tightens as it loses support. The outer cloud fades into a broader, colder haze. Across these layers, gradients smooth out. The smallest scales disappear behind the horizon. The larger scales keep stretching outward quietly and steadily. Next, attention moves from formation to the boundary itself. The event horizon becomes a point of no return that is not a surface. A boundary can be perfectly real even when it has no surface. The event horizon is real because it marks where outward roots stop existing. In that region, darkness is not a coat or a shell. It is the loss of a way back out. A faint glow can still circle nearby. Dust and gas can still curve in wide arcs. Yet a single invisible line divides two different futures. The scene holds on a quiet sphere of emptiness. Around it, a thin fog of light drifts in layered sheets. Some rays skim past and continue outward. Some rays lean inward and never return. The difference between those outcomes becomes sharper, closer in. The boundary is not made of matter, it is made of geometry. A clear idea anchors the boundary without adding mystery. Outside the horizon, an escape route exists for light. Inside the horizon, no escape route exists at all. The change is not gradual once crossed. It is a change in what directions remain possible. A small payoff arrives early and stays steady. The horizon does not pull like a net. It removes outward options from the set of futures. The physical detail that shows this is the narrowing of angles. Far away, light can leave in almost any outward direction and still depart. Closer in, only a small range of directions leads outward. That range shrinks as the boundary approaches. Near the threshold, it becomes a thin cone of possibility. Escape cone is the set of directions that still lead outward. It is like a patch of open sky that keeps shrinking. It matters because it turns escape into a question of geometry, not strength. A slow visual forms around that shrinking patch. A dim starfield sits behind the black center. The starfield bends into gentle arcs at the edges. The arcs tighten as they near the darkness. The bending does not require any material lens. Light behaves as if space guides it along curved tracks. Those tracks can be imagined as thin filaments. Some filaments loop once and then unwind outward. Some filaments spiral inward and end. The boundary is where no filament can unwind outward anymore. A second payoff follows soon after the first. The horizon is defined by paths, not by local texture. Two points can sit close together. One sits outside with outward paths available. One sits inside with none. Nothing locally dramatic has to happen at that divide. The boundary can be crossed without a flash. It can be crossed without a sudden change in density. It can be crossed without a shock. The meaning of the crossing is revealed only by the fate of signals. A signal would try to leave. It would find that all future paths still point inward. The scene shifts closer for a new anchor image. A faint ribbon of glowing gas curves around the darkness. The ribbon has a smooth gradient from bright to dim. The brighter side faces inward where heating is stronger. The dimmer side faces outward where energy thins away. The ribbon does not touch the horizon like fabric on a sphere. It swirls above it like mist above a deep drop. The boundary itself stays unlit because it has no material to shine. This is why the horizon is not a visible line in ordinary light. Only the behavior of nearby light can suggest where it lies. One number offers scale without strain. For a black hole formed from a heavy star, the horizon radius is about 30 kilometers. That is about the length of a quiet bay from one headland to another. The number is small compared to the star that once filled a vast space. The same mass becomes compact enough to remove outward routes for light. The scale shift continues in the opposite direction. For far larger black holes, the horizon can be enormous. The boundary can span a region larger than some planetary orbits, yet it remains the same kind of boundary. It is still the place where escape stops being a path. The change is in size, not in meaning. A new analogy holds the idea in the mind without tools or buildings. A river approaches a waterfall lip. Upstream, a drifting leaf can circle in slow eddies. Some eddies carry it back toward the calm water. Near the lip, the current narrows into a faster sheet. Past the lip, every track leads downward. No barrier blocks the leaf. The river simply stops offering a loop that returns upstream. The horizon is like that lip in the space of possible futures. Outside, some paths return outward. Inside, every path continues inward. The analogy is limited and it stays gentle. A black hole is not a fluid surface. A horizon is not a sharp edge that can be touched. The point is only the loss of return routes. Another payoff rests inside that limitation. The horizon is not an object that holds things in place. It is a boundary that separates what can communicate outward from what cannot. This is why the horizon is a one-way line for information. Light and any other signal share the same restriction. If a signal starts inside, it cannot reach the outside later. If it starts outside, it can still avoid the interior if its path stays wide. This turns the horizon into a causal boundary. Causal boundary means information cannot cross outward from inside. It is like a closed gate made of direction, not material. It matters because it defines what outside regions can ever learn directly. The scene slows again for a fresh visual anchor. A faint ring of light appears around the dark center. The ring is not a wall. It is a concentration of near-miss paths. Each near-miss path turns sharply and escapes. That turning happens in a tight region. The ring looks thin because many paths share similar curvature there. Outside the ring, the glow is softer and broader. Inside the ring, the darkness remains smooth. The contrast is the signature of a boundary that cannot shine. A limit of intuition enters with care. The horizon feels like it should be detectable at the moment of crossing. Ordinary boundaries leave marks. A shoreline has foam and a change in texture. A temperature boundary can be felt as a gradient. The event horizon does not have to show such a mark. For a large black hole, the local tidal stretching at the horizon can be gentle. No sharp local effect must announce the crossing. The real definition depends on the full set of future paths. That makes the horizon hard to confirm from local conditions alone. The limit is not only practical, it is built into the definition. Confirming a horizon requires knowing which signals can still reach far regions. That knowledge cannot be complete without a wide view of the entire space-time outside. This is a limit of observation and a limit of definition at once. Indirect evidence can still become strong. The curvature of light paths can be read outside. The missing region of rays can be mapped as a shadow. The horizon itself remains an inferred border rather than a directly marked line. Another payoff arrives as the inference becomes clearer. A horizon is not needed to bend light. Massive objects bend light even without horizons. The horizon is needed only to create a region from which light cannot return. That region creates a clean darkness with a bright rim nearby. The rim comes from rays that nearly fall in. The darkness comes from rays that do fall in. The difference between nearly and fully is a thin geometric threshold. This is why the silhouette stays stable even when the glow changes. A final slow image steadies the tone. The surrounding gas drifts in smooth layers. A faint haze scatters light into soft gradients. The dark center stays untextured and still. The boundary itself remains invisible yet decisive. Next, attention moves to what happens to light near that threshold. Curved paths and slowed time begin to share the same quiet geometry. Near a black hole, light begins to behave like drifting sand guided into curved dunes. The sky bends and timing slows because the geometry of space and time tightens. In that region, a distant glow does not travel on simple straight lines. It follows the straightest routes that the curved arena allows. A quiet scene appears. A single bright point drifts behind a dark center. As the pass becomes closer, the point stretches into a thin crescent. A second fainter crescent appears on the opposite side of the darkness. The two shapes hold steady for a moment. Then they slide and soften as the background changes. This first unlock is gentle and exact. The dark center announces itself by splitting and reshaping light that never touches it. The bending is not a tug that pulls a ray sideways. It is a change in what counts as straight when space itself is curved. The closer the pass, the more the route wraps around the center before escaping. The crescents grow longer because near-miss routes crowd together. Curvature turns diversity into a thin band of light. A new term can name this without burden. Gravitational lensing is light bending because space is curved by mass. Like wind wrapping around a cliff, drifting snow can arc along unexpected lines. Like that, drift bending does not require contact with the obstacle. The bend matters because it reveals mass through shape alone. The scene deepens with a slow checkpoint. The bright point slips closer to the dark center in projection. The two crescents stretch toward a near circle. A faint bridge of light appears between them. The bridge is not a strand of matter. It is a set of roots that loop longer before escaping. Some roots skim so close that they almost close on themselves. Those roots add a soft glow near the inner edge of each crescent. The inner edge looks sharper. The outer edge looks more diffuse. That difference is a physical detail of path crowding. Curvature produces a steep gradient in brightness. The gradient marks where escape becomes more difficult. Another unlock sits inside that gradient. The boundary is not needed for light to bend. Bending happens well outside the decisive edge. The boundary only guarantees that some routes do not return. The split crescents are created by near-miss routes that still escape. The darkness is created by routes that do not. This separation is clean in principle. Many routes cross similar regions and their departures can look alike. Time begins to lean in the same direction as light. Time dilation is slower passing of time near strong gravity. A slow image holds on a repeating rhythm in hot gas outside the boundary. A bright knot circles and produces a steady flicker. Near the dark center, the flicker remains regular in its own flow of time. Far away, the same flicker arrives stretched. 10 times slower is possible for signals that originate very close in. That is like a brief puff of mist lingering into a long and thinning veil. The closer the origin, the stronger the stretching. The effect is not a defect in the signal. It is the signal climbing out through deeper curvature. The light also loses energy in this climb. The glow shifts toward longer and softer colors. The pulse becomes broader and dimmer. Another payoff arrives here and answers a quiet question. Time dilation shows up as stretched spacing between repeated events. It shows up as slower pacing in any regular pattern. In that region, delay is built into the routes the signals must follow. Some signals wrap partly around the center before escaping. Longer path and slower time work together. Both effects can lengthen the arrival spacing. The scene changes again to keep the rhythm calm. A thin sheet of glowing dust drifts across the background. As it passes behind the dark center, the sheet warps into a snake-like ribbon. The ribbon narrows near the middle. It widens at the ends. The brightness is highest where the ribbon is narrowest. That is where many routes overlap. The physical detail is clear and quiet. The ribbon has a smooth gradient from bright spine to dim edges. It looks like a stream of light compressed by geometry. Now the scale shifts outward without breaking the tone. A small black hole bends light over a compact region. A far larger one can reshape light across a much wider span. The rule stays the same. Curvature guides routes. Near and far experience time at different rates. The difference is how quickly the change happens with distance. A steep change feels abrupt. A gradual change feels like a long slope. A limit of observation enters softly anchored in signal behavior. The strongest time stretching also makes signals faint. As pulses broaden, their peak brightness drops. They can sink into surrounding glow before a clean pattern emerges. Bending also mixes routes. Many different starting points can arrive along nearly the same outward direction. That mixing blurs a precise map of where each signal began. In addition, a haze of plasma around the region can scatter light. The scattering is gentle but persistent. It smears fine structure into a softer edge. There is also a limit set by distance itself. From far away, small features merge together. Even a perfect signal cannot carry infinite detail across vast spans. These limits do not erase the story, they shape what can be inferred with confidence. A final scene returns to the split crescents. The bright point passes closer than before. The crescents brighten then thin, their inner edges sharpen for a moment. Then the whole pattern seems to slow. Changes that are quick near the center arrive as slower drifts far away. The approach to the boundary can look like an endless easing. The final crossing does not appear as a visible step. It disappears into stretched time and fading light. Another payoff rests in this calm ending. The boundary is defined by routes. Light shows routes by tracing them. Time dilation shows routes by delaying them. Both effects tell the same geometric truth without needing a direct view inside. The next step moves from light alone to matter that misses the boundary and circles instead. Where paths crowd and sheer heat builds into a luminous disk. Near a black hole, matter rarely falls straight inward for long. It gathers into an accretion disk because sideways motion keeps shaping the fall. Accretion disk is a flattened flow that orbits while drifting inward. In that region, thin gas drifts in from many directions. Each stream arrives with a small sideways drift. That drift becomes rotation as the material moves closer. A calm scene forms from a wide view. A broad, flat whirl of faint glow surrounds a dark center. The glow is weakest at the outer edge. It grows brighter toward the middle in a smooth gradient. The first unlock is simple and steady. Rotation is not an extra feature that appears late. Rotation is the usual outcome whenever infall begins with any sideways motion at all. Material that starts with a sideways drift does not aim perfectly at the center. It curves around the center instead. Other streams curve in slightly different planes. Over time, repeated near misses crowd into a thinner band. The band becomes flatter because vertical motion is damped more easily than orbital motion. Collisions and mixing smooth the tilt into a common plane. From far away, the disk looks like a calm plate of light. Up close, it is a layered flow with a clear direction. A slow visual anchor settles in closer seen almost edge-on. The disk becomes a thin blade of light with a darker seam through its midline. The seam marks where material is thicker and more opaque. The top and bottom edges are slightly puffed. The brightness peaks near the inner region. It falls outward into a dim haze. Brighter knots appear where denser clumps pass through. They smear into arcs because everything shears as it orbits. Adjacent rings slide past each other at different rates. That sliding draws fine streaks and gentle layering across the glow. Angular momentum is the quantity that keeps rotation going. Like a spiral seashell that narrows inward while still turning, the disk can move closer only by redistributing its turning. The analogy stays gentle and limited. A shell only keeps a shape. The disk keeps exchanging motion between layers. Inner material must lose part of its rotational support. Outer material must gain it. The disk therefore acts like a conveyor of turning. Some rotation is carried outward while mass drifts inward. This is why a disk can feed the center without instantly collapsing as a whole. A second unlock follows and answers why the disk shines. Heat in the disk is not mainly from falling straight down. It comes from rubbing between neighboring flows. The rubbing is not solid friction. It is mixing in a hot plasma. Small eddies exchange momentum. The exchange acts like an internal drag. That drag converts orderly orbital energy into random motion. Random motion becomes heat. The heat then escapes as light from surface layers. Those surface layers are thinner. They allow radiation to leak out more easily than deeper regions. Another slow scene holds on the disk's layered skin. The upper surface glows smoother than the midplane. Fine gradients run from pale brilliance in the inner region to deep orange farther out. The lower surface mirrors the upper surface with faint symmetry. Between them sits a darker lane where optical thickness increases. Light from deeper layers scatters before it leaves. The result is a softened edge and a gentle blur. The disk does not show a sharp boundary. It fades into surrounding space through thinner and thinner veils. One number can carry the scale without strain. Near the inner disk, temperatures reach about 1 million degrees. That is far hotter than the surface of an ordinary star, which sits at only a few thousand degrees. The comparison is quiet but decisive. It explains why the inner disk can shine intensely, even when the central object stays dark. It also explains why color shifts with distance. Hotter regions radiate shorter light. Cooler regions radiate longer light. The disk becomes a temperature map drawn in brightness. A scale shift arrives without breaking the calm. The processes that stir the disk happen in small swirls that rise and fade quickly. Those swirls can be smaller than the disk thickness. Yet the disk as a whole can persist for years or longer depending on supply. The same system holds both timescales at once. Fast mixing shapes local heat. Slow inflow shapes the long arc of accretion. From far away, the disk looks steady and simple. Up close, it is a constantly changing fabric of moving layers. A faint knot can brighten and soften as it drifts through a hotter band. A faint ripple can travel as a spiral density wave, then dissolve into turbulence. A limit of observation enters softly and stays specific. The disk is not a clear window into its own interior. Much of its light forms in surface layers after many scatterings. Those scatterings erase the memory of exact origins. A bright patch can be the sum of many depths. Tiny eddies cannot be followed one by one. Only broad patterns in brightness and timing can be inferred. Even those patterns can be altered by thickness changes and ionization changes. This is a limit set by radiative transfer and turbulence. It sets a ceiling on how precisely the flow can be reconstructed from light alone. Another payoff rests inside that limit and keeps the story grounded. The strongest clue to inward drift is the brightness gradient itself. When emission rises steeply toward the center, energy release grows rapidly with depth in the gravitational well. That growth is expected when orbits become tighter and faster. The disk therefore acts like a visible bridge between far regions and the horizon. It converts gravitational binding energy into light before the point of no return. The black hole remains unlit. The disk becomes the luminous translator of the fall. A final visual returns to the thin blade seen edge on. The inner region looks slightly thicker, as if the glow swells where heating peaks. The outer edge looks ragged and faint. Thin streamers peel away into a diffuse cloud. The whole structure turns in silence. Light from the surface slips outward along curved paths. Some rays bend and return into the disk. Some escape and carry the smooth gradients into the distance. The next step moves closer to the narrow zone where light can almost circle the darkness. There a thin ring of roots begins to shape the shadow with unusual clarity. A dark center can appear with a bright edge even when nothing there emits light. The black hole shadow forms because bent light defines a missing region, then piles brightness into a narrow rim. In that region, the accretion disk glows in layered sheets. The inner layers shine more strongly. The glow fades outward into a thinner haze. Against that haze, a circular absence sits almost too clean. It is not a stain on a surface. It is a map of which light paths fail to escape. A slow scene settles. A broad field of dim radiance surrounds a central void. Near the void, a thin arc brightens into a sharp thread. The thread looks tighter than the surrounding glow. It curves nearly into a loop. The loop is not perfectly even. One side appears slightly stronger, the other side softens into a faint counter-arc. This early unlock stays steady. The shadow is not the horizon. It is larger than the horizon because many rays miss the horizon, yet still bend inward. Those rays turn away from the line of sight and do not reach far regions. The dark disk therefore marks a region of captured directions, not a material surface. Light behaves as if the space near the center offers fewer outward routes. The loss of routes begins before the boundary where escape becomes impossible. The shadow is the visible footprint of that loss. A second visual anchor arrives in the same calm. A thin veil of glowing plasma drifts behind the darkness like backlit smoke. The veil is smooth at large scales. Near the dark disk it becomes stretched into arcs. The arcs wrap around the edge and meet behind it. At the very rim, brightness tightens into a narrow band. The band looks like a bright seam sewn along the boundary of absence. The physical detail is a steep gradient. Brightness rises sharply at the seam. It falls smoothly away on either side. This contrast is the signature of light paths crowding together. The seam forms where many near-miss paths share similar curvature. Photon sphere is a region where light can orbit briefly. It is like a fog line that clings to one altitude on a mountain slope. Some wisps drift above and escape. Some sink below and fall into the valley. It matters because it creates a natural rim around the shadow. A small payoff follows in quiet clarity. The rim is bright not because the black hole shines. The rim is bright because many rays linger near the same radius before leaving. Each lingering ray spends more time near the center. It also bends through a larger angle. Those two effects crowd many paths into a thin apparent ring. The ring is not a solid structure. It is a census of routes that nearly close into loops. The loop is unstable. A tiny change in direction decides whether a ray escapes or falls inward. That instability sharpens the rim. It also deepens the interior darkness. Another slow image holds the instability as motion. A thin filament of light approaches the dark disk. It bends and slides along the edge like a ribbon caught in a slow whirl of air. For a moment it wraps partway around. Then it peels away and departs. A second filament arrives slightly closer. It wraps farther around and departs later. A third arrives closer still. It wraps almost into a full loop, then fades into the void. The scene shows a gentle ladder of outcomes. Each step inward adds more bending. Each step inward reduces the chance of escape. This unlock answers why the shadow size is stable. The boundary between escape and capture is set by geometry. It depends mainly on mass and spin, not on the disk's fine texture. One number can hold the scale of the rim. For a non-rotating case, the photon orbit region sits about 1.5 times the horizon radius. That is like a bubble that swells to half again its size. The detail matters because the bright rim is drawn outside the decisive edge. The rim can therefore be seen as a larger ring than the horizon itself. The shadow is larger still. The shadow includes rays that pass outside the photon orbit region and still fail to reach far regions. The disk can flare and dim. The rim remains tied to the same critical bending. A new visual anchor arrives with a wider view. The disk appears as a glowing plate with a dark bite taken from its center. Around that bite, the brightest arc hugs the edge like a thin shoreline of light. Beyond it, a fainter halo extends outward. The halo is not uniform. It has a smooth fall-off and a slight asymmetry. The asymmetry reflects motion in the emitting material. Yet the rim stays narrow. The rim stays sharply curved. The rim is a geometric edge cut into radiance. Another payoff arrives as the path structure becomes clearer. The rim includes light that has looped around the center once. Some light has looped more than once. Each extra loop adds delay and adds dimming. The loops stack into a series of ever fainter rings. Most of them blend together into a soft glow. Only the first strong rim stands out, the rest become a gentle thickening near the edge. This explains why the brightest feature is a single main ring. It also explains why the shadow interior remains smooth. The interior is not filled by a tangle of faint loops. Most looped paths either fall in or arrive too diffuse to build structure. The shadow therefore appears as an organized absence. A limit of observation enters softly and stays specific. The rim is narrow in angle. From great distance, many neighboring rays arrive from almost the same direction. They merge into one apparent line. Any fine subrings become difficult to separate. In addition, the glowing plasma around the center can scatter light. Scattering turns sharp edges into softened edges. It also mixes rays from different depths. The result is blur that does not come from distance alone. It comes from the medium the light must pass through. Another limit follows from variability. The disk can change brightness locally. Bright knots can drift. Those changes can mask the steady rim for a time. The rim is still present. It can be hidden under shifting foreground glow. This is why the shadow is best understood as a pattern, in paths not a single frozen picture. The pattern persists even when the lighting changes. Another slow scene returns to the rim's geometry. A thin sheet of light sweeps across the background. As it approaches the dark disk, it stretches into a curved arc. The arc brightens as it nears the rim. It thins into a tighter band. Then it breaks into two faint arms that wrap around and fade. The arms show bending without touching the interior. The band shows crowding near the critical region. The interior stays dark because those paths are missing entirely. Another payoff arrives in the same calm. The shadow is the simplest proof that gravity shapes paths strongly. It does not require knowing the disk's chemistry. It does not require knowing the disk's thickness in detail. It is a consequence of geometry that survives messy surroundings. The rim therefore acts as a ruler for curvature. It marks where near-miss paths accumulate. It suggests the depth of the well without entering it. The next step moves past the rim's outline and toward what lies beyond the boundary. Their direction itself turns inward and ordinary intuition begins to loosen. A boundary can be decisive even when it leaves no mark on the local scene. Beyond the event horizon, every allowed future points inward so no outward signal can ever return. At this distance, the boundary has no surface and no texture. It sits within faint glow and curved starlight like a change in current hidden under calm water. The change is carried by what paths remain possible. A slow scene holds on a dark sphere surrounded by a thin pearly haze. Outside the haze, stray rays pass in wide arcs and slip away into the starfield. Closer in those arcs tighten and begin to curl back. At the border, the last outward routes narrow to a thin set of directions. Just inside, the set collapses to none. A small unlock arrives early and stays firm. The horizon is a rule about futures, not a substance in space. Outside it, at least one outward future exists for a signal. Inside it, no outward future exists for any signal. Light behaves as the clearest messenger of this rule. If a pulse starts inside, every permitted route still leads deeper in. If a pulse starts just outside, a narrow set of routes can still reach far regions. This is why the boundary is a point of no return without being a wall. A second slow scene keeps the idea concrete. A sheet of faint glow drifts in layered bands around the darkness. Each band is smooth at first. Near the boundary, the bands stretch into long curves that lean toward the center. The closer the band begins, the less it can bend back out. The leaning grows stronger until outward curvature disappears. This physical detail is subtle and strict. The geometry creates a gradient in allowed directions. Far out outward, pointing directions are plentiful. Near the border, outward pointing directions become rare. Past the border, outward pointing directions do not exist in the future at all. The change can be pictured through a simple shape of possibilities. Light cone is the set of possible future directions for light. Like tall grass in steady wind, the set of future directions leans the same way. As the wind strengthens, the grass lies closer to the ground and stops standing upright. It matters because it shows why inward becomes the only future direction. The analogy remains gentle and limited. Space-time is not air and directions are not blades. The point is only the progressive tilt of what can happen next. Another payoff arrives as the tilt becomes more than an image. Outside the horizon, some direction still leads away from the center even if it is narrow. It might require a near-perfect aim, yet the option remains. Inside the horizon, every future direction still moves toward smaller radius. Even a beam aimed outward does not move outward in the sense that matters. It still advances toward the center as time advances. The inward fall is not a choice, and not a force added on top. It is the structure of the future. A calm visual anchor forms around that inevitability. A hollow globe of faint mist surrounds the dark center and makes space look almost tangible. Outside the globe, pale threads of light curve in many ways, and some threads unwind outward. Inside the globe, every thread slants deeper in and none of them level out. The mist stays smooth and quiet. The dark centre stays featureless. The only consistent pattern is the unified inward slant of every path. One number can ground the scale without strain. For a black hole, a few million times the sun's mass, a freely falling object reaches the deep interior in about 1 minute. That is like the time a long ocean swell takes to pass a rock. The comparison carries a deeper meaning without hurry. The fall can be brief along the falling path while distant signals stretch and thin. Far away changes near the border can arrive slowed and reddened. Intervals between repeating flashes can grow wider. The same sequence looks calmer and longer at great distance. A limit of intuition enters here with care. The horizon feels like it should be a dramatic boundary. Most boundaries are marked by texture or by pressure change. The horizon does not need such marks. For a large black hole, tidal stretching at the horizon can be mild. Curvature is still present, yet local conditions need not spike at the edge. Intuition built from surfaces can mislead. The decisive feature is not what is felt locally. The decisive feature is the global structure of future paths. A clear definition can name the destination without forcing a detailed picture. Singularity is the point where classical descriptions of space and time fail. Like a river narrowing into a gorge until smooth flow breaks into spray, a smooth description can end in a limit. Like ice cracking under growing stress, the old pattern can stop being reliable, even while the material remains. It matters because the classical theory stops giving trustworthy answers there. A limit of observation follows naturally and stays specific. No signal can be received from inside the horizon. This prevents direct confirmation of any internal sequence of events. Everything beyond the boundary must be inferred from what remains outside. Outside evidence includes the shadow shape and the disk glow. It includes timing patterns and the bending of light. Those clues can be strong, yet they remain indirect. Models must connect the outside patterns to the inside geometry. Those models depend on how matter behaves at extreme density and on how rotation shapes the interior. A final slow scene steadies the tone after that limit. Outside the boundary, a thin ring of glow drifts and flickers as hot gas shears. Inside the boundary, the same gas no longer contributes to outward light. There is no final flash that marks a crossing. The radiance simply stops arriving from that region. The shadow remains smooth, and the rim remains narrow. The surrounding haze continues to flow in layered arcs. In that region, the boundary is not an object. It is a change in what futures are available. A last payoff arrives as the view pulls back to the larger arc. The interior story is defined by inevitability of inward motion, not by extra violence. The boundary rewrites the meaning of outward by changing the structure of time and direction. Next, attention moves to a different effect that still reaches the outside. Gravity changes rapidly across short distances near the center. That change stretches and squeezes matter into long gradients and thin streams. A quiet difference in gravity becomes the most dramatic sculptor near a black hole. Tidal forces stretch and squeeze because gravity changes across short distances. In that region, the pull at one end of an object is not the pull at the other end. The difference can be small far away. It can become overwhelming closer in. A slow scene begins with a drifting clump of cold gas and dust. It is almost spherical at first. Its surface is smooth and faint. As it moves inward, the front side accelerates slightly more than the back. The sphere becomes an oval, the oval becomes a longer capsule. The edges blur into a thin mist. The first unlock is simple. The most important force is not the overall pull, it is the change of pull across the object's length. That change is a gradient. It acts like a quiet instruction that tells matter how to reshape. The stretching happens along the direction toward the center. The squeezing happens sideways. Both effects come from the same geometry. The clump does not need to touch the horizon for this to begin. It begins well outside, then steepens closer in. A second visual anchor settles in closer detail. The elongated clump develops a bright head and a dim tail. The head is denser and heats slightly from compression and collisions. The tail thins into a translucent filament. Fine strands peel away from the sides like pale smoke in slow water. The filament trembles in gentle waves. Those waves are not sound. They are changes in density as the material tries to hold together. The physical detail is a layered texture. Denser knots form along the filament. Between them, the filament narrows into faint threads. A small payoff arrives with clarity. Stretching does not mean the whole region becomes violent. It means the forces are uneven. Uneven forces create shape. Shape changes can remain smooth and quiet while still being extreme. Tidal force is gravity difference across an object's size. Like an ocean tide that lifts one end of a kelp ribbon first, the gradient pulls unevenly. Like that tide, the effect is gentle at first. Like that tide, it becomes stronger when the field changes faster with distance. It matters because it sets a natural limit on how close loose matter can stay intact. The scene shifts to a new checkpoint. A loose stream from an accretion disk drifts inward. It begins as a wide ribbon. Its thickness is uneven. It has brighter bands where density is higher. As the ribbon approaches, the near side gains speed. The ribbon twists into a tighter curve. Its midline stretches into a long arc. Sideways compression tightens it into a flatter strip. The strip becomes thinner and more sharply defined. The gradient of brightness steepens. The inner edge brightens. The outer edge fades. Another unlock settles in. The squeezing sideways is not a separate force. It is the companion of stretching. When the material is pulled longer, its cross-section tends to narrow. When gravity focuses trajectories inward, nearby paths converge and compress the flow sideways. This is why streams become filaments. This is why filaments become needles. The shape carries information about the field. A wider field produces gentle elongation. A steeper field produces long, thin strands. One number grounds the change without hurry. If the distance to the center becomes about 10 times smaller, the tidal difference becomes roughly 1,000 times stronger. That is like drifting from the wide mouth of a whirlpool into its narrow throat. Small variations that once felt negligible become the dominant pattern. The scale shift follows naturally. A clump that spans kilometers can be reshaped in moments near the inner region. The same black hole influences orbits across millions of kilometers over much longer times. The same rule applies at both scales. The difference is how quickly it changes with distance. Another slow scene holds on a single fragment that begins to break apart. It is not a brittle snap. It is a progressive thinning. The fragment forms a chain of beads along a filament. Each bead is denser. Each gap is thinner. The filament between beads becomes almost transparent. The beads drift farther apart as stretching continues. The beads also flatten slightly as sideways squeezing persists. The physical detail is a repeating pattern. Bright knots alternate with dim bridges. The pattern appears because the material cannot remain smooth under strong gradient and shear. Another payoff arrives quietly. There is a point where self-gravity and internal pressure cannot hold against the gradient. Past that point, the object cannot behave as a coherent whole. It becomes a stream of parts. Those parts can still interact. They can collide and heat. They can radiate if outside the horizon. Yet the original object is no longer a single structure. This explains why disruptions can feed disks. It also explains why a disk can gain a fresh supply of long filaments rather than neat spheres. A limit of intuition enters with care. The stretching is often imagined as a clean pull into one perfect line. Real flows are not perfectly aligned. Rotation tilts trajectories. Pressure spreads material sideways. Turbulence stirs knots and gaps. The result is not a single tidy strand. It is a braided network of filaments with different densities. Intuition prefers simple shapes. The field produces complex textures. The difference matters because simplified pictures can hide the true range of outcomes. Another limit follows and stays specific. The most extreme stretching can occur close to the horizon or inside it. Light from inside cannot return. Light from very near the horizon can be delayed and dimmed. Scattering in hot plasma can soften sharp details. These effects limit what can be directly observed in the final stages of disruption. Inference relies on timing patterns and on how brightness shifts with radius. It also relies on how line shapes broaden due to fast motion. Those clues can match more than one internal configuration. Models must choose between them. The uncertainty is not a lack of care. It is built into signal loss and limited resolution at great distance. A new checkpoint returns to visible geometry. A wide spiral arm in the accretion flow develops a thin spur. The spur curves inward and stretches into a long thread. The thread wraps partially around the dark center, then fades into the inner glow. The outer disk remains broad and softly layered. The inner region becomes sharper and more filamentary. The transition marks where gradients steepen. Another payoff rests in that transition. Tidal effects do not act only on loose objects. They also shape the disk itself. They contribute to shear between neighboring rings. They help create narrow streams that carry mass inward. They also help set where stable structures can exist. The same gradient that forms the shadow rim also forms the filament rim. Geometry links these features into one calm system. The final visual anchor steadies the pace. A thin filament passes behind the dark center and reappears as a fainter strand on the other side. Its brightness is not symmetric. Its inner segment is tighter and brighter. Its outer segment is looser and dimmer. The difference reflects deeper curvature and stronger stretching closer in. The scene remains quiet and continuous. The next step shifts from stretching alone to twisting. When the black hole rotates, surrounding space gains a slow swirl. That swirl changes how orbits lean and how energy can be extracted from the flow. A spinning black hole changes the space around it into a slow twist rather than a simple drop. Rotation drags nearby space along, so motion becomes partly forced even before any orbit begins. At this distance, the accretion disk looks familiar at first. A flat glow circles a dark center. Yet the glow is not symmetric in its behavior. One side appears slightly sharper, the other side appears softer and more spread. The scene holds on a dim torus of haze that sits just outside the horizon. Within that haze, thin streamlines curve in the same sense. They tighten toward the center. They also lean as if the entire region is turning. The first unlock is calm and direct. Spin does not add a new force. It changes the geometry that defines what counts as still. Frame dragging is the twisting of space near a rotating mass. Like slow currents in tree sap near a rotating knot nearby, paths begin to drift the same way. Like that drift, the twist is strongest closest to the center. Like that drift, the effect fades with distance until it becomes negligible. It matters because even an object with little sideways motion gains a sideways drift from the arena itself. A second visual anchor deepens the same idea. A thin ribbon of glowing gas falls inward from the disk surface. It starts wide and soft. As it approaches the inner region, the ribbon begins to spiral. The spiral is not only a choice of the ribbon. The spiral reflects the turning of the background geometry. The ribbon becomes narrower. Its inner edge brightens into a tight seam. Its outer edge blurs into a faint veil. A small payoff arrives with that seam. Rotation makes the inner region behave like a moving floor. Even attempts at straight inward motion are deflected into a swirl. This means the disk can approach closer in a stable way when rotation is strong. It also means the bright inner edge can sit nearer to the horizon. The glow becomes more compact. The brightness gradient steepens. The whole system looks tighter even when the supply of gas stays similar. A single number gives scale without urgency. Near the inner disk, speeds can reach about 100,000 kilometers per second. That is fast enough to span a large planet's diameter in a moment. The number is not the point by itself. The point is that fast motion makes light patterns sensitive to direction. Brightness can concentrate on one side due to motion and curvature together. The glow can be skewed without changing the central darkness. The scene shifts to a slower checkpoint that names a key region. Ergosphere is a region where space is forced to rotate. It is like a whirl in a fog bank where stillness cannot be held. It is like a leaf that cannot remain fixed because the water beneath it keeps sliding. It matters because energy and angular momentum can be exchanged there in unusual ways. The ergosphere sits outside the horizon, and it has a distinct boundary. The boundary is not made of matter. It is traced by where forced rotation begins to dominate the idea of rest. Inside it, no path can remain stationary relative to distant stars. Outside it, stationary paths can exist again. A slow visual holds on that boundary. The torus of haze becomes slightly brighter at its outer rim. The rim looks like a thin contour line in a dim atmosphere. Streamlines within the rim all curl the same way. Streamlines outside the rim can point in more directions. The physical detail is a changing curvature pattern. Inside the ergosphere, outward paths still exist, but only with a shared sideways drift. The sideways drift is not optional. It is embedded in the structure of the region. Another payoff follows with a gentle mechanism. The ergosphere allows a flow to lose energy, while another flow gains it even without a solid surface. A fragment of plasma can split into parts. One part can fall inward with reduced energy relative to distant space. Another part can escape with increased energy. The horizon is not crossed by the escaping part. The exchange happens outside. This is why rotation can power energetic phenomena without treating the black hole as a glowing object. The disk and its fields provide the visible channels. The rotating geometry provides the deeper reservoir. A new visual anchor settles on the inner disk edge. The edge is no longer a smooth circle. It appears slightly displaced toward one side. Bright knots shear into curved streaks. The streaks align with the direction of rotation. A thin lane of darkness separates the brightest arc from the central shadow. That lane is not empty space. It is a region where fewer light paths reach far regions. The gradient across the lane is steep. It marks the rapid change in curvature close to the boundary. The scale shifts outward to a wider view. The forced swirl near the horizon is a small region compared to the full disk. Yet that small region can influence patterns across the entire flow. Tiny changes near the center can alter how heat is released farther out. Over longer times, the disk can precess and warp. A gentle wobble can travel outward like a slow wave. Over much longer times, still accretion can spin the black hole up or down, depending on how material arrives. The same geometry holds from seconds near the inner edge to ages of gradual feeding. A limit of observation enters softly and stays specific. Spin is not observed directly as a rotating surface. It is inferred from light patterns and timing patterns outside the horizon. Those patterns depend on disk thickness and on plasma scattering. They also depend on viewing angle and on turbulence. Different combinations can mimic similar asymmetries. The inner edge location can be blurred by changing opacity. The bright arc can shift as knots move. This creates model dependence in spin estimates. There is also a resolution limit at great distance. Fine structure in the ergosphere region can merge into one broader glow. The result is a confident picture of forced swirl in general, but uncertainty in exact degree. Another payoff rests inside that uncertainty. Even when the exact spin is uncertain, rotation leaves a consistent signature. It compresses the brightest region inward. It skews brightness in a preferred direction. It changes the timing of flickers and the curvature of arcs. These changes can be compared across many situations. Each comparison refines the story without claiming a direct look at the engine. The final visual steadies the pace. The torus of haze turns like a slow braid around the dark center. Streamlines curl within it. Outside it, the disk remains broad and layered. The shadow stays calm and circular in its absence. The surrounding glow carries a slight twist that never fully disappears. Next, attention moves to how disks and fields can focus outflow into narrow beams. Rotation sets the stage for jets that carve long, thin lines through space. A narrow beam can rise from the brightest chaos without becoming a wide spray. Jets form when fields and rotation guide plasma into a tight column along the spin axis. In that region, the accretion disk glows as a flattened whirl. Above and below the disk, the glow thins into a faint corona of hot plasma. The corona is not uniform. It is layered with brighter patches near the inner rim and dimmer haze farther out. From the inner regions, two pale pillars begin to appear. They are not solid structures. They are streams of energized particles and fields that remain confined to a narrow channel. The first unlock is simple. A jet is not a straight fall turned upward by force. It is an outflow that becomes narrow because the surrounding conditions favor a particular direction. Magnetic field lines act as guiding threads in a plasma. Like iron filings lining up around a hidden magnet, charged particles tend to spiral around these invisible threads. Like a ribbon of mist drawn into alignment by a steady wind, the flow becomes ordered along the field direction. It matters because it explains how a beam can stay narrow without walls. A slow, visual anchor settles close to the disk. The inner disk looks like a bright ring with a steep brightness gradient. Above the ring, faint loops of glowing plasma arch upward and back down. The loops are not sharply drawn. They appear as soft arcs with brighter cores and dimmer edges. Within the arcs, thin streamlines run upward. The streamlines tighten into a column. The column has a bright spine and a dim sheath. The spine is narrow and steady. The sheath is broader and more diffuse. The physical detail is a layered structure within the beam. Brightness falls from the spine outward in smooth steps like nested veils. A small payoff arrives in the way the beam stays narrow. A jet remains collimated when the field geometry pinches the flow toward the axis. Collimation is the focusing of a flow into a narrow beam. It resembles wind funneled through a mountain pass. The wind begins broad. The pass narrows the available paths. A long banner of cloud then stretches straight beyond the gap. The jet differs in substance, yet the idea of guided paths holds. It matters because it turns a wide, messy environment into a clean direction of escape. The scene shifts to the base of the beam. The inner corona brightens and becomes more structured. Thin filaments rise from the disk surface and join the column. The column does not start as a rigid rod. It starts as a braided bundle. Strands twist around a shared axis. They merge and smooth as they climb. The brightness pulses along the spine in gentle knots. Each knot is a region where the flow compresses and heats. Each knot fades as it expands into the next segment. Another payoff settles here. The jet is powered by energy available outside the horizon. The disk releases gravitational energy as heat and light. Rotation in the inner region can also provide an additional reservoir through the twisting of fields. The black hole itself does not need to emit. The jet draws its order from geometry and its energy from the surrounding plasma and fields. This is why the beam can coexist with the darkness at the center. The center remains a missing set of outward roots. The beam is a route that stays outside those missing paths for long enough to escape. A new visual anchor appears farther from the base. The beam becomes straighter. It narrows into an almost constant width. A faint corkscrew pattern winds around it. The corkscrew is subtle. It shows as alternating bright and dim patches on opposite sides of the column. The sheath looks slightly uneven. The spine remains the brightest line. The physical detail is a slow helical texture that suggests twisting fields. The surrounding medium is darker and more diffuse. Where the beam touches that medium, a thin boundary layer forms. It is a soft edge rather than a sharp border. Another unlock arrives and removes a quiet confusion. The jet is not simply matter launched and left alone. It stays in contact with fields as it moves. The fields carry energy and momentum. The plasma responds by spiraling and streaming along the guided direction. This is why the jet can accelerate and stay narrow at the same time. Acceleration can happen gradually as magnetic tension and pressure gradients push along the axis. The idea remains calm. The beam does not require a sudden kick. It can build speed over distance while staying organized. One number can hold the scale without strain. A large jet can extend about 100,000 light-years. That is like a ribbon long enough to wrap around a planet many times. The scale shift is gentle and clear. The launching region sits near the inner disk, where distances are small compared to a star's orbit. The same outflow can then cross the span of a galaxy and beyond. In the near region, the beam is a narrow column near a bright ring. In the far region, the beam becomes a long line etched across intergalactic darkness. The same guiding idea stretches from compact to immense. A slow scene follows the beam outward. The spine begins smooth, then develops a chain of bright beads. Each bead is followed by a slightly dimmer segment. The beads are not evenly spaced. They drift and change. Some grow brighter and then soften into the background. The physical detail is a repeating pattern of compression zones. These zones arise when the flow encounters changes in external pressure or internal variability. The flow compresses and heats, then re-expands. The resulting glow becomes a series of knots along the beam. Another payoff arrives with this bead pattern. The jet carries information about the engine through timing and structure. Even far away, the chain of knots reflects changes that began near the base. A disturbance can travel along the beam and leave a bright mark where it compresses. The mark can fade as the beam stabilizes. This provides a natural way for distant regions to echo compact changes without any direct message from inside the horizon. The echo remains outside the boundary. A limit of observation enters softly and stays specific. The launching region is wrapped in hot plasma that can be opaque at many wavelengths. Scattering and absorption smear fine structure into smoother glow. In addition, the beam near the base can be so narrow in angle that distant views merge it into a single line. Fine substructure within the spine becomes difficult to separate. The field itself is not directly visible. Its presence is inferred from how the plasma aligns and from how light prefers certain orientations. Those clues can be strong, yet they can also be mimicked by turbulence and changing density. Models must choose between them. The limit is set by opacity distance and the indirect nature of field inference. Another slow visual anchor steadies the tone after that limit. The beam widens slightly into a faint cocoon. The cocoon is a soft envelope of heated material around the spine. It has a smooth brightness fall-off and a gentle edge. Beyond it, the surrounding medium shows a dim cavity where the beam has displaced and heated it. The cavity boundary looks like a faint arc. The arc is broad and slow, like a distant wavefront frozen in place. Another payoff rests in this wider view. Jets do not only shine, they reshape environments. They can push back surrounding gas and carve channels. They can deposit energy far from the center and change how future material moves. This links the smallest region near the horizon to the largest scales of a galaxy. The beam becomes a bridge between compact curvature and vast structure. The ending remains gentle and stable. The two opposing beams extend in opposite directions. One appears slightly brighter than the other because of direction and speed effects. Yet both share the same narrow spine and layered sheath. The disk continues to glow below them in smooth gradients. Next, the story widens to how black holes grow and how their surroundings respond over long times. Feeding and merging begin to shape the largest centers of galaxies. Growth near a black hole can be slow and steady or sudden and bright depending on how gas arrives. A black hole gains most of its mass by accreting surrounding material through a disk and inner flow. In that region, a galaxy core appears as a dim whirl of dust and plasma. Broad lanes of haze curve inward like a pinwheel. The lanes become thinner closer in. The inner glow rises into a compact ring and then fades into a central shadow. This early unlock stays calm. A black hole grows when orbiting material finds a way to lose angular momentum. That loss lets matter spiral inward rather than circle forever. The disk is the mediator. It converts orbital energy into heat and light. It also transports the ability to keep orbiting outward. A second scene slows down to show the transport. The disk surface is smooth at large scales. Closer in, it becomes streaked with thin spiral ripples. Each ripple is a denser band. Each band shears into a longer arc as inner rings move faster than outer rings. The brightness has a steep gradient. It is brightest near the inner edge and softer farther out. This is where mass can drift inward without a sudden plunge. The drift is not free fall. It is a gradual leakage through a turning flow. A small payoff arrives here. The same processes that heat the disk also enable growth. The heating is not a side effect. It is the signature of energy being released as matter moves to tighter orbits. The release can be gentle or intense. It depends on density, thickness, and magnetic structure. When supply is thin, the disk can be faint and hot. When supply is thick, the disk can be bright and cooler at its surface. The center remains dark in all cases. The light comes from outside the horizon. A single number can ground the long view. Under steady, near maximum feeding mass can double in about 50 million years. That is about the time a river can carve a broad new valley bend. The comparison is not exact in mechanics. It holds only the sense of a slow but decisive reshaping across deep time. The scale shift continues. Near the inner edge, patterns change over seconds and minutes. Farther out, the same disk can persist for millions of years with gradual variation. Small flickers ride on top of a long, slow growth. A quiet analogy holds the long arc without adding human scenes. A snowdrift deepens in a sheltered hollow as wind brings more crystals. The drift does not deepen because the hollow wants snow. It deepens because geometry and flow guide what arrives. In the same way, the black hole grows because the surrounding environment channels matter inward. The channel can open or close as the galaxy core evolves. It matters because growth is not constant. It is episodic and shaped by large-scale structure. A new visual anchor widens the view into feedback. Around the central glow, a hot halo of thin gas fills a broad region. Within that halo, two vast cavities appear above and below the disk plane. Each cavity is a dim hollow with a bright rim. The rim is a compression front where gas is denser and hotter. The cavities look like two gentle bowls carved into a fog. Their edges are smooth. Their interiors are quieter and fainter. The first unlock of feedback remains simple. Outflows can reduce inflow by heating or pushing surrounding gas. Jets and winds do not need to carry most of the mass. They can carry enough energy to change the environment. A narrow beam can pierce the halo. A wider wind can inflate the cavities. Both effects can lower density near the center and slow future accretion. The process is not a single blast. It is a cycle. Inflow builds a bright inner flow. Energy release drives outflow. Outflow alters the supply. Supply changes the brightness again. Another payoff arrives in the shape of the cavities. The bright rims show where a pressure wave compresses the halo. The interior hollows show where gas has been displaced. This makes feedback visible as geometry. The center influences far regions without direct contact. Energy travels outward through plasma and fields. The halo responds by reconfiguring into new gradients. Over time, those gradients guide later inflow along new routes. The system becomes a conversation between small scales and large scales without any voices. A third scene returns to the disk and shows how the inner region can switch states. The disk thickens slightly near the center. A faint corona rises above it. The corona is patchy. It has brighter knots and dimmer gaps. The knots shift as magnetic structures rearrange. The disk surface becomes more turbulent. Its smooth spirals break into braided streaks. This unlock answers a quiet question. Feedback can be triggered not only by more supply. It can be triggered by a change in magnetic ordering. When fields become more aligned, a jet can strengthen. When fields become tangled, the jet can weaken and heat can spread more isotropically. The same mass inflow can produce different outflow patterns depending on internal organization. A limit of observation enters softly and stays specific. The growth rate cannot be read directly from the center because the inner region is often obscured by thick dust and scattering plasma. Light leaving the inner disk can be absorbed and re-emitted at longer wavelengths. That process erases timing and blurs the original spectrum. In addition, different combinations of inflow rate and radiative efficiency can produce similar outward brightness. A faint system can be underfed. It can also be efficient at hiding its light in hot, thin plasma. A bright system can be overfed. It can also be briefly boosted by shocks and compression. This creates degeneracy in inference. Only broader patterns across time and across environments can reduce it. Another scale shift steadies the tone. Over a single orbit near the inner edge, the disk can heat and cool and rearrange. Over millions of orbits, the halo can inflate and relax. Over hundreds of millions of years, the galaxy core can supply new lanes of gas or starve the center. The black hole mass changes slowly compared to the flicker of its surroundings, yet the cumulative change can be vast. A final visual anchor gathers the section into a calm tableau. The central shadow remains clean and untextured. Around it, the disk glows with a steep brightness gradient. Above and below the halo shows two broad cavities with bright rims. Faint ripples travel outward along those rims as pressure equalizes. The whole structure suggests a cycle rather than an endpoint. The next step moves to another path of growth that does not rely on steady inflow. Black holes can also gain mass when two dense centers merge and their horizons settle into one. Two black holes can approach each other without light, then reshape space in a way that travels outward. A merger radiates energy mainly as gravitational waves, leaving one calmer black hole behind. At this distance, the scene begins with two dark centers, separated by a wide gulf of thin gas. Each center is surrounded by a faint curved haze. The haze is not a neat disk. It is a soft envelope with dim streamlines. The streamlines arc inward and sweep around each darkness in slow curls. Between the two centers, the haze thins into a narrow bridge. The bridge brightens slightly as it compresses. It stretches into a long, translucent filament. The filament is the first physical clue of uneven gravity. One end is tugged more strongly than the other. The filament narrows. It becomes a thread with a brighter spine and a dimmer sheath. The two shadows remain distinct, yet their surrounding curvature begins to overlap. Light behaves strangely near each center. Rays passing between them bend into S-shaped paths. Some rays wrap partway around one shadow, then drift toward the other. The geometry looks like two wells whose rims begin to touch. Gravitational wave is a traveling ripple of space-time curvature. Like ripples on a still lake after two stones fall close together, the disturbance spreads outward as expanding rings. The analogy stays limited and careful. Water moves through water. Space-time changes the distances that define motion itself. The point is the outward traveling pattern, not a material wavefront. The pattern strengthens as the two centers draw closer. The orbit tightens. The time between repeats shrinks. The surrounding haze responds by forming curved wakes behind each shadow. The wakes are not symmetrical. One side of each wake is sharper. The other side is softer and more diffuse. The change is driven by speed and by the shared gravitational field. The spiral becomes faster near the end. There is a clear reason for the speed-up. Energy and angular momentum leave the system as gravitational waves. With less angular momentum, the orbit cannot remain wide. With less orbital energy, the separation cannot remain steady. The pair therefore spirals inward rather than circling forever at the same distance. This is the calm engine of inspiral. Nothing needs to push the black holes together from outside. The system loses orbital support by radiating curvature away. A new slow image holds close to the midpoint between the shadows. The bridge filament splits into two thinner threads. Each thread wraps toward one center. Each thread forms a hook shape as it bends. The hooks are stretched and smoothed by shear. They appear as pale arcs with a steep brightness gradient along their inner edges. The outer edges fade into fog. The arcs drift inward and disappear into the inner darkness around each center. The arcs show the last stable routes for surrounding material. They also mark where tidal forces sharpen rapidly with distance. The approach is not quiet in geometry, even if the light remains faint. The space between the shadows becomes a corridor of extreme curvature. Paths that once passed cleanly between them begin to loop. The corridor narrows. The available routes reorganize into a tighter set. This answers why the final approach accelerates. The tighter the orbit, the stronger the gravitational wave emission becomes. The stronger the emission, the faster the orbit tightens. The process feeds itself until only a few orbits remain. One number can anchor that late stage. For stellar mass black holes, the final rapid phase can last about 1 second, like the time a ripple spreads across a small pond. The scale shift is gentle and wide. Near the pair, the final changes unfold in moments. Far from the pair, the same event spreads into a long, weak pattern that continues outward for ages. The disturbance becomes a vast expanding shell of subtle stretching and squeezing. It moves through interstellar gas and dust without needing to push them aside. The shell is not a blast wave in matter. It is a change in space-time that matter simply follows. A second visual anchor arrives as the merger moment approaches. The two shadows draw so close that their surrounding haze merges into one warped envelope. The envelope looks like a single oval of dim glow with two darker pits inside. The pits circle rapidly. Their paths carve a brightened track in the surrounding haze. The track is not a ring of matter. It is a region where light paths linger and where gas compresses. The pits then become one. For an instant, the central darkness is not perfectly smooth. It appears slightly dented, as if the shadow edge is trying to settle. A thin, bright rim forms around the new shadow. The rim is uneven at first. It has a few brighter arcs that drift along its circumference. These arcs fade as the rim becomes more uniform. Ringdown is the fading vibration of space-time after merger. Like a deep lake after a strong disturbance, the surface patterns simplify into smoother rings and then vanish. The analogy holds the sense of settling toward a simple shape. The new black hole does not need to oscillate like a solid object. The surrounding space-time relaxes into the steady geometry of a single rotating black hole. The relaxation radiates away remaining irregularity as gravitational waves. The rim in light can mirror that settling by becoming smoother and more stable. The surrounding haze also calms. Filaments that once fed the bridge are torn and dispersed. The brightest compression zones soften into a broader, dimmer glow. The center becomes quieter in appearance, even though the event has changed the system profoundly. A limit of intuition enters softly here. It is tempting to imagine the gravitational wave as a wind that pushes on objects. That picture misleads. The wave does not carry matter along like a flow. It changes distances in a rhythmic pattern as it passes. Objects can be stretched and squeezed relative to each other, yet there is no preferred direction of transport in the way a wind has. The effect is also tiny at large distances. The disturbance spreads over an ever larger sphere. Its influence on any small region becomes extremely subtle. A limit of observation follows from the same geometry. The wave carries a clean summary of the orbit and the masses. It does not carry a direct image of what happens inside the horizons. It also cannot uniquely describe every detail of spin orientation and surrounding plasma. Different configurations can produce similar outward wave patterns once averaged over distance. The surrounding light can add its own variability. Turbulence and scattering can mask the faint rapid changes near the final moments. This forces inference to rely on broad consistency rather than complete detail. The calm story remains intact. The outward travelling ripple is real. The precise internal picture remains partly hidden by the horizon and by distance. A final scene steadies the aftermath. One shadow remains at the centre. Around it, a thin glow reforms into a new disk plane. The plane can be tilted relative to the previous orbit. The inner rim becomes a narrow arc. Its brightness gradient steepens toward the centre. Above and below, the surrounding haze shows faint cavities where earlier motion has cleared channels. The overall shape becomes simpler with time. The new black hole sits as a stable absence within organized light. The next step widens the perspective again. Mergers and long feeding both leave traces in how galaxies evolve across deep time. Those traces appear in the distribution of mass, heat, and motion far from the central shadow. A dark center can shape a whole galaxy without ever shining on its own. The influence comes from how accretion releases energy that changes surrounding gas. At this distance, a galaxy core appears as a soft bulge of starlight wrapped in dust lanes. The lanes curve inward in broad arcs. They narrow into a faint, uneven ring near the center. Inside the ring, the glow becomes compact and steep. Then it fades into a quiet shadow. The first unlock arrives early. The black hole affects growth around it by regulating how easily gas stays cold and dense. When gas cools and settles, inflow strengthens and the inner region brightens. When the inner region brightens, outflow and heating strengthen. Those effects then reduce how much gas can settle. The cycle does not require perfect balance. It only requires that energy release changes the conditions for future inflow. A slow visual anchor steadies the idea. The central ring looks like a dim necklace of clumps. Each clump is denser and darker at its core. Each clump has a faint outer veil that glows softly. Between clumps, gaps open like narrow inlets. Through those inlets, thin streams drift inward as pale threads. The threads curve and shear. Their inner edges sharpen. Their outer edges dissolve into haze. A small payoff rests in the gaps. Inflow is not a uniform flood. It is a set of favoured channels that open and close as pressure and turbulence shift. That is why the central brightness can vary while the larger galaxy seems steady. The next checkpoint deepens the mechanism without urgency. Heating can come from radiation from the inner disk. Heating can also come from mechanical outflow in jets and winds. Both forms act on gas by raising its temperature and pressure. When pressure rises, gas spreads and becomes less able to fall inward. When pressure falls, gas can condense into denser lanes again. Feedback is the loop where energy release modifies the future supply. Like a river delta that shifts its channels after each season, the flow chooses new paths as the landscape changes. The river does not aim for a channel. The slope and sediment determine the route. In the same way, gas does not aim for the center. The gravitational field and pressure gradients determine where streams survive. It matters because a galaxy core can alternate between calm and active without external triggers. A second visual anchor moves above the ring. A faint hourglass of luminous mist rises along the axis perpendicular to the disk plane. The hourglass is narrow near the center and wider farther out. Its edges are soft. Inside it, the mist is slightly brighter, as if the region is thinner and hotter. Around the waist of the hourglass, the ring remains flattened and clumpy. The physical detail is a boundary where the hourglass meets the thicker halo. That boundary appears as a faint arc that curves outward. The arc marks a compression front where gas piles up. Another payoff follows gently. Outflow does not need to remove much mass to matter. It only needs to deposit enough energy to change the phase of the gas. Warm gas resists collapse. Hot gas expands and lowers density. Cooler gas can return later as it radiates energy away. This creates a duty cycle. Activity can come in episodes. Between episodes, the galaxy core can look quiet while conditions slowly reset. One number holds the scale of the reset. A cooling and settling phase can take about 100 million years, like the time a large storm system can reshape a coastline over many cycles. The comparison is only about patience and accumulation. The physical process remains different. The scale shift stays calm. Near the inner ring, clumps can rearrange in thousands of orbits. Farther out, the halo responds over times that dwarf individual disk fluctuations. The same core can flicker on short times, while its long-term impact unfolds slowly. A third visual anchor widens outward to show the halo response. The halo is a dim sphere of thin gas with faint ripples. The ripples form concentric shells that are slightly brighter at their edges. Each shell is a region of compressed gas. The interiors are quieter and darker. The shells are not perfect spheres. They are distorted by the galaxy's broader structure. They bend and stretch along the disk plane. They appear smoother along the polar direction. The physical detail is a gradient in brightness across each shell edge. The edge is sharper on the side facing the core. It is softer on the far side. Another payoff arrives with that gradient. A galaxy can carry the memory of central activity as layered structures in its halo. Even after the core dims, the halo can remain hot and puffed up. This can reduce the return flow of gas. Star formation in the inner region can then slow because the reservoir becomes harder to access. The black hole does not need to dominate the galaxy's mass to influence the galaxy's future. The influence is levered through temperature and pressure. The next checkpoint addresses a quiet regularity. Across many galaxies, the central black hole mass tends to track properties of the surrounding bulge. This is not a strict rule in every case. It is a tendency that points to self-regulation. When the bulge is deeper and denser, it can confine hotter gas more effectively. Confinement allows more gas to reach the center. More inflow allows more growth and more feedback. Feedback then pushes back until the supply becomes harder again. The loop can settle into an approximate relation over long times. Another visual anchor returns to the inner ring with a new detail. The ring becomes slightly warped. Its near side tilts upward. Its far side dips downward. The clumps slide along the warp and collide at the line of maximum bend. At that line, the glow brightens into a thin ridge. The ridge is not a new object. It is a compression zone where streams converge and shock. The ridge then breaks into smaller knots that drift inward as filaments. Another payoff rests in the warp. The galaxy core does not need a smooth disk to feed the center. Irregular geometry can enhance transport by forcing collisions and shocks. Collisions dissipate orbital energy. Dissipation allows material to move inward. This makes growth possible even in messy environments. It also makes feedback messy. Outflows can be asymmetric. Heating can be uneven. The result can be a core that alternates between different shapes and channels rather than repeating the same pattern. A limit of intuition enters softly. Intuition prefers a simple picture where stronger activity always means stronger growth. The loop is more subtle. Strong activity can reduce the future supply by overheating the reservoir. Weak activity can allow gas to pile up and later produce a stronger episode. This can create delays between cause and effect. It can also create oscillations that are not strictly periodic. A limit of observation follows and stays specific. Many visible signatures of feedback come from gas and dust far from the horizon. Those regions respond to multiple influences at once. Turbulence, cooling, and gravity all shape the same structures. Light from the center can be absorbed and re-emitted, which blurs timing. Outflow can carve channels, yet inflow can simultaneously refill them along different lanes. This makes it difficult to infer a single causal chain from a single snapshot. Inference improves by comparing shapes across scales, and by following how shells, warps, and filaments align over time. The section ends on a calm, wide view. The hourglass mist fades into the halo. The halo shells soften into the background. The inner ring remains clumpy and warped, still feeding faint threads inward. The central shadow stays unchanged in its silence. Next, the perspective shifts farther back in time. The earliest black holes and their environments reveal how seeds form and how rapid growth becomes possible in the young universe. A dark center can appear very early, long before a galaxy looks mature. The early universe can grow black holes quickly when dense gas finds a low-resistance path inward. At this distance, the scene begins inside a young compact cloud. The cloud is thick and uneven. It holds braided filaments of colder gas. Between filaments, warmer haze fills the gaps. The filaments converge toward a dim core. The core is not bright. It is a region where the glow steeply fades. A thin curved edge surrounds it like a rim of pale mist. Dust grains drift through the filaments like mist in still air. Near the rim, the dust forms a shallow gradient. It is denser on the inner side. It is thinner on the outer side. The gradient marks a boundary where inflow becomes organized. The darkness does not need to be large to matter. It only needs to deepen the local well, so drifting gas begins to spiral. Spiral motion appears as a slow turning of layered haze. The outer layers move in wide arcs. The inner layers tighten into smaller circles. Here the first plain fact settles in place. In that core, a boundary exists where outward paths quietly run out. A drop of rain striking soft sand makes a small hollow. A later gust slides more grains into that hollow. The hollow grows without any extra carving. In the same way, a small central pull can guide more inflow toward itself. An accretion disk begins as a flattened swirl in the cloud. An accretion disk is a flattened flow orbiting a compact center. The disk is not a solid sheet. It is a stack of rings with a temperature gradient. The outer rings stay cooler and darker. The inner rings brighten and thin. Light behaves as a tracer that follows this layering. A band of glow wraps around the core like a narrow belt. The belt is brightest where the flow is hottest. The belt fades where the flow is cooler. A second quiet fact arrives with the belt. Brightness can resist further inflow. Radiation pressure is outward push from light on matter. When the inner rings shine hard, gas feels a gentle outward shove. The shove slows the inward drift. The drift does not stop everywhere. It finds paths through denser streams and through cooler pockets. The disk breathes between these states. It thickens for a time, it thins for a time. Each change sets a new balance between inward pull and outward light. The visual anchor shifts closer. Within the bright belt, tiny clumps form and dissolve. They leave faint streaks that curve with the rotation. These streaks show that the flow is turbulent. Turbulence mixes hot and cool layers. Mixing changes how efficiently the flow radiates. That efficiency decides how much mass reaches the core per unit time. A single number can hold the scale of this race. About 1 billion years can pass while a young galaxy assembles its main structure. That span is like enough time for a mountain range to soften into rounded hills. In that long interval, many short episodes of inflow can occur. Some episodes last only a brief orbital cycle near the core. Others last for many rotations in the outer rings. The scale shift is gentle. Seconds near the inner rim become eons across the host galaxy. Over those eons, a seed black hole can become massive. Growth comes from two main channels. One channel is steady, inflow through a disk. The other channel is the joining of two dark centers after galaxies combine. Such a joining leaves a sharp signature in motion. The disk can become warped. The warp is a twist in the plane of rings. It looks like a ribbon that changes its tilt with radius. The twist shows that angular momentum has changed direction. Mass and spin carry the memory of these changes. Spin is the stored rotation of the black hole. Rotation reshapes where stable orbits can exist. When spin is high, the inner edge of the disk can sit closer in. Closer rings run hotter and radiate more strongly. When spin is low, the inner edge sits farther out. Farther rings stay cooler and dimmer. This simple link helps explain why similar masses can show different brightness. The scene drifts outward again. Beyond the disk, gas spreads into a thicker envelope. The envelope has a mottled texture. Some regions are clearer. Some regions are opaque with dust. Light leaving the inner belt must pass through this uneven veil. Along the way, it can be absorbed and re-emitted at different wavelengths. It can also be scattered into softer halos. Here, a limit of observation becomes unavoidable. Different combinations of dust thickness and disk temperature can produce similar outgoing light. A distant signal would carry only the final filtered pattern. That pattern can hide whether the core is small and obscured or large and exposed. The limit is not mystery. More than one cause can fit the same effect. Time adds another veil. As the universe expands, waves stretch and redden during travel. Features that begin sharp become broader and weaker. Small fast flickers can blur into a slow glow by the time the light arrives far away. The constraint remains real. Only what survives the journey can be known from the signal alone. Yet the journey also grants a gift. Very distant light begins its travel when the universe is young. It carries a snapshot of early conditions. The snapshot is not complete. It is still enough to reveal that some black holes grow early and fast. The visual anchor returns to the core one last time. The rim of mist appears almost still. Inside it, the bright belt slowly thickens and thins. Outside it, filaments continue to deliver fresh gas. The whole system resembles a quiet weather pattern in 3 dimensions. Flow lines curl inward, layers shear past each other, heat rises and fades into the envelope. The calm insight settles with the motion. Black holes do not only end stellar lives, they also record the history of how matter moves through galaxies. In the next section, the view widens to the far future of these records. The tone stays gentle as the last perspective comes into place. A black hole becomes clearest when attention rests on the shapes made by light. The event horizon is a boundary where outward paths for light end. Outside that boundary, a faint glow can still circle. It gathers into a thin belt. The belt shows a steep brightness gradient. The inner side looks sharp. The outer side looks soft. A dark hollow sits at the center. The hollow is not a surface. It is a region where light fails to return. The belt can look lopsided. One side brightens while the other side thins. The bright side often forms a clean crescent. The dim side fades into a wider, quieter smear. At this distance, the dark center looks larger than the boundary itself. That mismatch points to curved light paths. Some paths skim close and still escape. Some curl around and escape after a longer loop. The escaping light stacks into a thin rim near the hollow. The rim is not a wall. It is a crowd of roots that nearly repeat. The rim tends to sit about 3 times farther out than the horizon. That spacing is like the third ripple that spreads after a raindrop lands on still water. The dark hollow therefore marks bending, not a hard edge. The image stays slow and concrete. A glowing belt circles a central absence. The belt is not smooth. It shows streaks that follow curved tracks. Each track narrows as it approaches the dark center. Brightness drops over a short distance. Around that drop, the thin rim flashes as a delicate thread. It brightens, then fades. It returns with a slightly different thickness. The thread is made by light that almost circles back on itself. When the belt shifts, the thread shifts with it. The hollow stays steady as the belt shimmers. Behind the belt, distant light is folded into arcs. A background field of faint points stretches into thin curves. Some curves meet and close into a pale circle. The circle encloses the hollow and the belt. The folding is the same rule seen farther out. Curved space guides paths. It turns a straight beam into an arc. It can also split one source into multiple arrivals. The circle appears when many routes share the same outline. The arcs can also appear as 2 opposing crescents. Their curvature always points back toward the central absence. The circle can look smooth. It can also look patchy along its length. Small bright knots can appear where routes pile up. Then the knots soften as the alignment drifts. A quiet scene from nature holds the feeling of the geometry. A mountain valley sits at dawn. Mist drifts across a dark floor. Ridges redirect it into long streamers. A deeper hollow gathers mist into a denser band. The mist never reveals the ground itself. It reveals the slopes by how it flows. In the same way, light never reveals the event horizon. It reveals the curvature around it. The belt traces the steep inner slopes. The pale arcs trace the wider landscape. A calm limit arrives and stays. The event horizon never sends a return signal. No light climbs out once a path crosses the boundary. So the boundary is not seen directly. It is inferred from patterns outside it. The hollow depends on missing light. The rim depends on near-repeating routes. The belt depends on hot material that remains outside. Each of these can change with time. Clumps drift. Brightness rises and falls. Fine detail blurs because light arrives from a range of depths and angles. Changing patches overlap in time. A stable outline comes only from consistent agreement across many changing moments. It is a conclusion built from repeated shapes. It is not a visible seam. Light carries another lesson on the way out. Near the boundary, gravity stretches time. Light that climbs outward loses energy. Its color shifts toward the red end. The shift grows stronger closer to the boundary. The belt can therefore show a gentle color gradient. Inner regions tend toward deeper reds. Outer regions tend toward less shift. The gradient looks like a slow ramp across the belt. It has no hard step. It turns brightness into a soft spectrum. This is not paint. It is a record of climbing out of a deep field. The record arrives already blended across nearby layers. That blending sets another quiet limit. Only a range is carried, never a single perfect value. A scale shift eases in. The belt is small compared with a star. It is smaller still compared with an orbit around a star. Yet bending reaches far beyond the bright belt. Farther out, a passing beam can still be nudged. It can arrive delayed because it takes a longer curved route. It can arrive doubled because paths split around the mass. Over large distances, slight bends add up into broad distortions. A wide region becomes subtly warped for a long time. Even when the belt grows dim, the warp can remain. The hollow can stay recognizable even when the glow thins. Another limit remains gentle. The rim can never be traced with infinite sharpness. The reason is not only distance. The rim is built from routes that almost repeat. Any small disturbance breaks that near repetition. A small change in the belt shifts which routes are bright. The hollow edge also relies on many near misses. If near misses blur together, the edge blurs. A perfect outline would require perfectly steady light. That steadiness is not guaranteed in a moving environment, so the rim is thin but not absolute. It is delicate but persistent. It appears when paths line up, then softens when they wander. The wide view returns in silence. The pale circle sits faint behind the scene. The central hollow remains dark. The rim stays as a thin thread along the edge. The belt glows outside it as a soft band. Small brightness bumps drift and fade along the band. The background arcs hold longer, then shift by a little. Sometimes the circle breaks into two opposing crescents. Sometimes it closes again. Everything changes without any sudden jump. The boundary itself does not need to show. Its presence is carried by the way paths curve. The scene settles. A dark hollow rests at the center. A thin rim clings to its edge. A wider belt glows beyond. Behind, faint points stretch into pale arcs and then relax. Nothing needs to cross the boundary for the boundary to matter. The boundary is present as an absence that shapes what remains. A black hole is recognized by what it does to paths, not by a visible surface. The glow can dim, the arcs can fade, the quiet outline can remain.